Next topic is MapReduce. As we talked about, the vanilla Hadoop technology is made up with two core technology. One is HDFS, which we just learned, and that second one is MapReduce. HDFS is for distributed storage, while MapReduce is for processing. So here we are going to talk about MapReduce operational architecture. We'll talk about the generic MapReduce concepts. Then we are going to see the programming model for Hadoop MapReduce. And then we are going to learn MapReduce framework. We are going to see an example of word count. So here we are going to use MapReduce program to count how many times a particular word occurs in a file. And then we are going to see how we can execute MapReduce application. Here we are going to do one in Eclipse and the other one at the command line. And we are going to talk about input file and input format. I think one of the questions that was asked was, when the file was read as an input to MapReduce, Hadoop MapReduce, how that file is going to be split into, multiple data nodes and things like that, okay? So that is done, in fact, the what is called the input format class. In Hadoop, everything is customizable. It comes with a bunch of built-in classes. By the way, Hadoop is built with Java. So it comes with a bunch of default implementations. However, you can customize a lot of Hadoop behavior, okay, by providing custom implementation of those Java classes. And we're going to do some of those in this code camp. Okay, so some of these contents are from Yahoo website on the Creative Commons Attribution 3.0 license. So let's talk about Hadoop MapReduce operational architecture. So as we learned, MapReduce is made of a single job submitter. I'm sorry, the job tracker as a master node, and then multiple task tracker nodes. Those are slave nodes. Okay, so again, just like HDFS, MapReduce has master and slave architecture. So master is a job tracker node, and task trackers the nodes that actually perform the tasks, and they are slave nodes. And there is a client that actually submit the jobs to job tracker. So client submit the job tracker, and job tracker will actually divide the work into multiple task tracker nodes. So this is an execution flow. So client submit a job to job tracker, and job tracker creates execution plan. It will decide how it's going to divide the work and which task tracker will be assigned to perform that job. And job tracker submit these works to task trackers, and then task tracker performs this task and report progress to job tracker via heartbeats again. And job tracker manages the map and reduce phases. So MapReduce, as we are going to learn in detail in the following slide, is made of two phases. One is the map and reduce. In fact, there is another phase in the middle, which is called what is called the sort and shuffle phase. So, three phases: map and sort and shuffle, and the reduce phases. These phases are being handled by job tracker. And then when the job is done, job tracker will update the status of the job. So this picture actually shows the architecture. So client program will submit a job to job tracker. So this job tracker will assign this task to task trackers, okay? And it will coordinate this map and reduce phases. And by the way, this map and reduce phases are all handled by the task tracker, okay? So you can think of this is the in the middle here. The first tier is a map phase, and the second tier is a reduce phase. And these lines those are sort and shuffle phase, and sort and shuffle is done by Hadoop MapReduce. So you don't have to get involved in sort and shuffle, but you have to provide your logic, map logic, and as well as a reduce logic. So you have to provide mapper and the reducer code, okay? And now the files are going to be splitted. So these are split 1, split 2, and split 3, and things like that. And so, I think one of the questions that was asked is how these files are in fact being splitted. That is the job of input format class. Okay. the input format class will split these files, and in this case, task tracker 1 will receive split 1 and split 4. Okay, and then it will perform mapper functions, map. Okay, and then it might actually perform what is called the partition and combine. So the this is extra step, and then the task tracker number 2 will do the same thing, task 3 will do the same thing, and then the output of the mapper will be in fact combined and partitioned and sorted and shuffled, okay, in the middle, okay, and then the task tracker will perform the reduce function. Okay, and then output will be created into output file 1 and output file 2. Okay, so later on when we actually perform MapReduce when you run the MapReduce application, the output is going to be like part 0, 1, 0, 0, 0, 0 and part the 0, 0, 0, 1. So you will in fact have a multiple output files, and the reason is because different task tracker will generate its own output files. Okay. All right, so exercise 0 is we are going to learn MapReduce architecture. So let's take a look at the lab documentation. So I have already unzipped the MapReduce. So I'm going to take a look at the index HTML file. Okay, so this is the lab documentation. Let me increase the font size a bit. Okay, so exercise 0 is study the MapReduce operational architecture. So, again, if you click the Cloud Manager, you are going to see MapReduce 1 here, and it is in good health, and it is made of 1 job tracker and 1 task tracker. Okay, so again, we are working with a single node. That's the reason we see only one single task tracker, but typically you are going to see multiple task trackers in production environment. Okay, and you can take a look at the, so you can actually see they are in good health. Okay, so if you click the status, you're going to see them in good health. Okay, now we are going to study some configuration of job tracker and task tracker. So we are going to click the configuration, and you can see view and edit. And we are going to see job tracker configuration. So if you click this guy, and let's see, so yeah, we are going to see port and addresses. So the port for job tracker is 8021. Okay, so that is, and you can take a look at the task tracker configuration as well. Okay. Now you can find out the status of the jobs using job tracker web UI. Okay. So let me actually show that in myself. So here I am going to the Hadoop job tracker. So you should see this link. Okay. So if you click this guy, you are going to see several categories of jobs. So you probably seen running jobs. If jobs are running, okay, you are going to see running jobs. These are the retired jobs, meaning these are completed, and it's basically it's not being tracked on. Okay, you can actually, and then there are completed job as well. Okay, so I have done, I have run many jobs. Okay. So you can certainly take a look at the job status. So, I'm going to just click any of this job, okay? And you are going to see information about the job, okay? So how many map, task it is being performed, how many reduce, so whether that is successful or not. Yeah, in this case, I haven't done, it didn't actually perform reduce, but it actually performed map. Okay. Typically, you're going to see both the map and reduce, but in some cases, you're going to see just map it is done. Okay. And file system counters, how many bytes are read, and how many bytes are written, and all those things. Okay. So we're going to actually talk about these things in a bit more detail after we run our MapReduce application. But you can actually see your job information from this the Hadoop job tracker page. Okay, so that's basically point 3 exercise. Okay. Okay. Let's see. Right now it's actually 2:37. We could actually have 12 minutes break time, and then we'll actually start from 2:50. And or if you guys actually want to continue, we can actually finish earlier. Instead of finishing 4:40, 4:20, 4:30, we can actually finish like a 4:15. So let me know what you guys want to do. You want to actually continue, or you want to take a break? Okay. So let's talk about MapReduce concepts. So these are generic MapReduce concepts. The basic concept of MapReduce works like this. So you can think of MapReduce as a programming model designed for processing large volumes of data in parallel by dividing the work into a set of independent tasks. Okay. So MapReduce programs are written in a particular style influenced by functional programming construct. Okay, so specifically idioms for processing lists of data. So these days, the concept of functional programming is actually very popular, and MapReduce is in fact based on this functional programming concept or construct. So let's talk about it a bit. So MapReduce uses a functional programming. So the reason it needs to use a functional programming is because computation of large volumes of data need to be performed in parallel. Otherwise, it's going to take a too long time. Okay, so by dividing the work, dividing the data into parallel, and then dividing the work on those data in parallel fashion, you can actually achieve a high performance. Okay, and these works are done by large number of commodity machines. Now, non-functional programming model, which we are familiar with, basically in non-functional programming model, the shared data, all the processes are sharing the data. Now, this non-functional programming model would not work to handle large, the large data set, okay? Because the communication overhead required to keep the data on the node synchronized at all time is very high. Okay, so we need to have a functional programming model. In the functional programming model, the data is not shared, and basically, you have input and then you get the output, and this is all done independently. So MapReduce uses the functional programming model where all data elements in the MapReduce are immutable, meaning that they cannot be updated. So there is no need to do synchronized shared data among processes. So if a mapping task you change input pair, key value pair, it does not get reflected back in the input files. So input files do not get changed. In functional programming model, it will just generate an output. Okay, so input files do not have, they do not mutate it. They do not get mutated. So there is no reason to, synchronize the shared data. There is no data to be shared in the first place. Okay, which are then forwarded by Hadoop system into the next phase of the execution. Okay, so this is how functional programming model is used in MapReduce. Okay, so the map and reduce functionality, basically you can think of them as list processing. So you can think of MapReduce program performs a transformation of list of input data elements to list of output data elements. Okay. So in MapReduce application, this transformation is done twice. One is in mapping phase and the other in the reducing phase. Okay, and we're going to actually talk about what mapping phase does, and we're going to actually talk about what reducing phase does. Okay, so you do this transformation of list of input data elements to list of output data elements in mapping phase, and then you're going to actually do the same thing, the same transformation in reducing phase as well. So you can think of this mapping phase using this example. So there is an input list. Okay, so this is input list, and then mapping is done in the middle, then it will generate an output. So a list of data elements are provided one at a time to a function called the mapper, which transform each element individually to an output data element. Okay, so you can think of, for example, the one task, node, tasks, yeah, one, yeah. So the one task tracker will actually perform like these three, the first three. And the next task tracker will perform the next four, maybe. And the last task tracker will actually perform, these two. And each of those mapper function will generate the list of output. Okay, so that's mapping phase. So suppose if you have a two-upper, so what you want to do is you want to convert every single word in a file, in a text file, to uppercase. Okay, then you might in fact have a mapper function, which is called, let's say, two-upper, which returns the uppercase version of its input string. So you could use this function to turn a list of strings into a list of uppercase strings. Okay. So in this case, we are not modifying the input strings, but we are generating output that are converted. Okay, so this is basically an example of functional programming. Okay. Reducing phase lets you aggregate values together. So you have a list of items, and the reducer function receives the iterator of these input values from an input list, and then it will combine these values together, returning a single output value. Okay, so this is the reason why it's called the reducer. Okay, and we're going to actually see example code in a few minutes. So reducing list example. So reducing is often used to produce summary data. So, but when you say aggregation, summary is actually one example of that, or minimum or maximum value. Those are other examples of aggregation. Turning a large volume of data into a smaller summary of itself. And so plus reducer can be used to reducing a function to return the sum of the list of input values. So these are generic concept of MapReduce. We haven't really talked about how this concept is actually being applied into Hadoop MapReduce yet. Okay, so that's something we're going to actually talk about here. So Hadoop MapReduce programming model. So this is, you have to actually provide mapper and reducer code. So here we are going to actually learn how we can do that using Java code. So Hadoop MapReduce framework takes these concepts and uses them to process large volumes of data or information. So again, MapReduce program, when you create the MapReduce program, you have to provide two code. One is called the mapper. That is the one that implements the mapper functionality. And reducer is the code that implements the reducer functionality. Okay. Both mapper and reducer takes input data, then generate the output data. Okay. So mapper will receive the input data, then it will generate the output data, and that output data will be fed into reducer as an input data, and the reducer will actually generate the output data. Between the mapper and reducer, there is another phase called the sort and shuffle, and that's something we are going to talk about in a few minutes. By the way, every data element in Hadoop, excuse me, is in the form of key value pair. Okay, so it's not single value, it's always key value pair. So remember that. So this is important concept in MapReduce. Every data element is in a form of key value pair. So for example, if I have a log of time-coded speedometer readings from multiple cars, they could be key value pair. So in this case, the first column, that is the keys. Okay, and then the rest of the data could be value. Okay, so we have a key, we have a key and value pair. Okay, so remember this. Every data element in MapReduce, Hadoop MapReduce, is in the form of key value pair. Okay. Okay, so this is another example how Hadoop MapReduce data is flowed. Okay, so on the top you have the set of input data, and this input data will be split into multiple mapper function. So each mapper will take the data. Okay, so in this case, it will be split by the job tracker into different mappers, and the mapper will generate key. By the way, you can see everything in Hadoop MapReduce is in the form of key value pair. Okay, so in this case, the first mapper will generate key value pair of A1 and B2. So in this case, the black node key and the white node value is the value. Okay, same thing for the mapper 2, mapper 3, and mapper 4. Okay, and then these output will be shuffled and sorted and shuffled. Okay, so after these values are sorted and shuffled, you might actually have input as you might in fact have these values. For A, it does have a value of 1 and 5, and the B, it has a value of 2 and 7. So, this is B2 and B7. And the C, it has a value of 2, 9, and 8. Okay, so shuffle and sort or aggregate, this phase will actually perform against the output from the mapper, and then it will feed this data into the reducer. And reducer will, in this case, probably, I think in this case, yeah, so this code is basically trying to find out what is the largest number. So in this case, the largest number for A is 5. And for B it is 7, and for C it is actually 8. And this X, Y, and Z, again, this is representing just another key. It could be the same value of A or B or C, but it's just representing a key. Okay. Now in this case, you have to provide code for the mapper. However, this shuffle and sort and aggregation will be done by Hadoop. And then you have to provide your reducer code. So when you are writing MapReduce application, you have to create the mapper code, and you have to provide the reducer code. Okay, so this is another, the slide that actually shows how these key value pairs are being generated and fed into the next phase. So mapper is applied to every input key value pair, and the mapper will generate intermediate key value pairs. Okay, so K1, K1 and value 1 will generate a list of K2 and V2. These intermediate key value pairs are sorted and shuffled and grouped by the key, so it will actually generate, for oops, sorry about that. For the list of K2 V2, it will generate the K2 and list of V2. Okay, so if you actually go back to the slide over here, basically we are generating a list of A and list of B and list of C, right? And then reducer is applied to the sorted and shuffled and grouped intermediate key value pairs, and so this will be fed into reducer, and reducer will actually generate the list of another key value pairs. Okay. Yeah, it might be a little bit confusing to you guys for now, so we are going to actually look into these things actually using various sample application later on. So if you don't understand what I'm talking about here, don't worry about it too much. Okay, so that's the programming model, and we haven't actually seen the program yet, so we're going to actually take a look at the actual code later on, after we talked about the MapReduce framework. So MapReduce framework takes care of distributed processing and coordination. So it does handle scheduling, so jobs are broken down into tasks, which are then scheduled. And the task localization of the data, so the task, in this case code, is going to be moved to the node that contains the data. Okay, so framework sends the task to nodes that host segment of data. It also handles error handling. So if a job failed, then it will try the job. I should use the term task in this case. If a task on a particular task tracker node failed, then it will retry on other task tracker nodes. Data synchronization. So it does perform sorting and shuffling of the data, and then it moves data between nodes. So I think I have actually a picture over here. Okay, here we go. So we have by the way, each node in fact you can think of data node and task tracker nodes actually running on the same machine. Okay, so this is the data being splitted. Okay. They're actually present in the data node, and each mapper will take this splitted data, and so the output will be sorted and shuffled, and this data could be actually moved around to different nodes. Okay, and this is going to be grouped and the grouped input data will be fed into reducer, and the reducer will generate an output. So this is the output from reducer 1. We're going to call it part 0, and this is the output from reducer number 2, so part 1. Okay, and anything, even the result will be replicated, right? So anything that you save in HDFS should be replicated, okay, whether that is in output or input, doesn't matter. So this is basically showing the same thing. So we have multiple nodes, okay, and so mapping process will receive these input data key value pairs. It will generate the output key value pairs. Output key value pairs will be sorted and shuffled, and in that case, the data might be moved around to different nodes, okay, and then the nodes, then the data will be fed into reducer, and then it will generate an output. Okay, and this sorting and shuffling and all those things are done by Hadoop framework, so you don't have to worry about it. So you as a developer has to provide just a mapper function and the reducer function. So we are going to take a look at word count. So this is the this is sort of the hello world example for Hadoop MapReduce. Okay, so we are going to use the this example. Okay, so basically what you want to do is we want to count how many times each word occurs in a set of files. Okay, so in our sample application we have two files. One is called the foo.txt and the other one is a bar.txt. So these are two input files we want to process. We want to see how many times a word occurs in these two files. So in this case, we want the after MapReduce application is performed. We are going to see sweet will occur. It should have a 1. This occurs twice, right? Here, oops. So the this occurs twice, and bar occurs just once, and the file occurs 3 times, and foo occurs twice, and in occurs 1. So basically, after performing MapReduce, the functionality, we should actually have an output like this. Okay, so this is word count application. So the logic is like this. In the mapper, basically for each word in the file contents, we want to generate a word, and then, so again, everything is in the form of key value pair, right? So, basically the word is the key and 1 is the dummy value. So every word will occur just once first in the mapper. And then reducer will aggregate that. Okay, so reducer will aggregate. So, basically there is a sort and shuffle phase in between, and then it will actually it will feed a word and the values. So in this case, it will have like the word 1, 1, 1, 2, if 1, 1, 1, if it occurs 3 times or something like that, and it will just sum the value. Okay. All right, so that might be a little bit confusing. So let's go to the next slide, and we're going to actually see the actual example code. So the mappers and reducers in Hadoop in this example. So several instances of the mapper functions are created on the different nodes on the cluster, meaning different task tracker will have several its own mapper function. So in this case, each instance, each mapper instance will receive a different input file. It is assumed that we have many such files, and the mapper emit the word 1 as pairs as an output. So suppose we have these 2 files. So these are the 2 files. So the input element to word count mapper is gonna be key value pair, right? So for text file, the key value is gonna be offset of the file. Sorry about that. Offset from the file, and then the value is going to be content of the file. So in our foo that text file, the 0 is the offset from the file, and the content is going to be, the value is going to be sweet. This is the foo file. And the second line start from the offset 28, and the content is the second line. Okay. So in this case, output element from the word count mapper function is going to be the word 1, 1, and word 2, 1, word 3, 1. Every node, every word should have a 1. Okay, as an output of the mapper as a key value pair. So what we are going to see is like a suite one, this one, the one, foo one, file one, this one, and is one, and the one, and something like that. Okay, so this is the output from the mapper. Okay. All right. Now, the reducer will be invoked, but before reducer is invoked, it will be sorted and shuffled and aggregated. Okay. So the reducer will actually receive this data. So word 1, because word 1 occurs twice, and word 2 occurs 3 times, word 3 occurs just once. So in our test data, suite 1 has just 1, and this one, because it just occurs once, the occurs 3 times. So it will have 1, 1, 1. Foo occurs 1, 1, and file occurs 1, 1, right? Okay, so this is the input to the reducer. So this is generated by Hadoop, the sort and shuffle and aggregate phase. Okay, and then output from the word count reducer is going to be suite occurs just once, and the occurs 3 times, and foo occurs twice. Okay. So just to repeat what I just talked about, several instances of reducer method are also instantiated in the different nodes in the cluster, meaning different task tracker will have a different set of reducers, right? Each reducer is responsible for processing the list of values associated with the different words. So it receives these values, okay, here. And the list of values will be the list of ones. In this word count example, the reducer sums up these ones into final count associated with a single word. The reducer then emits the final word count. So this one, suite, comma occurs once, the occurs 3 times, and foo occurs twice, and things like that. Okay. Okay, so when you write this code, you are going to provide mapper class that represent the mapper, and then you are going to write the reducer code, which is representing reducer, and then you might want to build a driver code. So driver, you are going to create a job, and then you are going to submit the job. And when you're submitting a job, you have to specify the name of the mapper class and name of the reducer class. Okay. So this is the mapper class. So this is the mapper class, and we have a generic, so key in, value in, key out, value out interface. So basically, the key value pairs represented is going to be, is generic type, object text and int writable. Okay, and it has to implement map method. Okay. So map method will receive key value pair and the context. So this context is the context object you are going to use to create an output. So in this case, basically what we do is that we are going to get, by the way, this map method will be invoked for each line of the file. Okay. So in that case, the key is going to be offset value, and the value is going to be contents of that line. Okay, so what we do here is that we are going to screen tokenizer. So we are going to convert into, by the way, this this text type is Hadoop type. So we have to convert it into string. Okay, so you convert it into string, and then we are going to use a screen tokenizer, and then we have the screen tokenizer, which is actually a list of words. Okay, and then basically we are just checking for each word. We are going to generate an output. So basically, the output is going to be key value pair. The key is going to be the word, and the one is one is basically one is the constant value of 1. Okay. Sorry about that. The constant value of 1. By the way, int writable, these are not really Java type. This is actually Hadoop's version of int type. Okay. All right. So this is the mapper class, which is generating list of word, and value is always 1 for that word. Okay. Now this is the reducer code. So by the time reducer class is invoked, it's going to be in the form of this. Okay, because Hadoop will actually take the output from the mapper. It will sort and shuffle, then it will group things. So it will actually provide this as an input to the reducer. So reducer will actually receive the word as a key, and then it will actually have, iterator of these values, 111 or 11 and 11 and things like that. Okay. So that is the reducer. So you can see, it's receiving text as input key value and the iteratable of int writable. So you can see this is 11 or 111 depending on how many times the particular word has occurred. Okay, and again, it's actually using context object for generating an output. So in this case, we are basically generating the sum. Okay, so it goes through in a loop of these values. Okay, so it will just get the value of this values iterator, and it will just, if there are in fact 3 ones in this iterator, it will actually have a 3 as a sum. Then it will write the word the has the value of 3 as a value of the key. Okay, so this word is a key, and the sum, how many times that particular word has occurred, is a value. So that will be output from the reducer, and that's what you're going to actually see as an output. So this is a reducer class. Now you have to also provide the driver class, and driver class is basically you create a job, and you are providing name of the job. So this is the name of the job that you are going to see in the job tracker. So when you actually search for a particular job, you can actually use this name. You can actually search for this name to find out the name of to find the job. Okay. And then you have to set up MapReducer classes. So you are going to set mapper class and set reducer class, and you provide the class object for the mapper and reducer, which we just created in the previous slide. So this is the reducer class. This is a mapper class, and we have to actually provide the class object to the job. Okay. And here we can actually set number of reduced tasks. So in this case, we're actually setting to 1 because we have only one reducer. But you might actually specify the higher number if you have a multiple the task tracker nodes. And then you are going to submit a job. So you say job and wait for completion, and then it's basically submitting a job, and it will return the success or failure. Okay. If it returns 0, that is a success. 1 is a failure. Okay, so we have learned what MapReduce is all about from a conceptual perspective. You also see programming model in Hadoop, how you can actually build mapper and reducer code. Okay, now let's see how we can actually execute MapReduce application. So there are 2 different ways we are going to exercise running MapReduce application. One is within an Eclipse, okay, and then the second option is at the command line. Okay. The difference is that when you are running MapReduce application within Eclipse, the default file system is a local file system. Okay. Now, if you want to use HDFS as a file system, then you have to provide a full path of your HDFS. So, for example, if I want to use input directory of HDFS, then I have to specify HDFS : localhost 8020 and /user cloudra my data input. So this is how you can specify HDFS when you're running inside Eclipse. When you're running the application at the command line, the default file system is a HDFS. So in this case, if you want to use a local file system, you have to actually provide file notation. Okay. At the command line, you have to actually create a jar file first. So in our exercise, you're going to create the jar file first, and then you are going to use Hadoop command. So you're going to say Hadoop and jar, and then you specify name of the jar file that contains your Java classes, and then you have to specify the main method of your you specify your the driver class. And then you specify the input directory and output directory. In this case, as a default, these are all HDFS directories. Okay, so when you are running in at the command line, make sure you are dealing with the HDFS. When you're running inside Eclipse, you're dealing with local file system as a default. Okay, so input and output directory. So an input can be either directory or file. Okay, so if it is a directory, then all files under that directory will be used as input files. If you specify input as a file, then that file is going to be used as input file. Okay, so in the case, you have a single input file. If you specify directory, then you could have multiple files underneath that directory. Output is always a directory. Okay, as we learned before, the output is going to be created by multiple, let's say, reducers, right? So, in this case, multiple reducers will generate a different the output file, right? So these output files is going to be created on the output directory you specify. Okay. So now, if output directory already exists, Hadoop will generate an error. Okay, it will generate an error indicating output directory is already existent, so I cannot write the data into it. Okay, so in our code, just as the convenience, we added code to delete the output directory always whenever we the executing the code. So we just check whether the output directory exists and we delete first. So if you actually comment this code, then you are going to see an error message if the output directory already exists. Okay, so one of the exercises I'm going to ask you guys to do is to comment these 3 lines of code and see what happens. Okay, finally we have exercise 1. Okay. So that's exercise 1. Okay, so we are going to import sample application. I provided sample application as a Maven project. So all you have to do is just import Eclipse, import the Maven project into Eclipse, and then you are going to run the application using files in the local file system, and we are going to take a look at the code, and then we are going to run it into we are going to actually copy these test files into HDFS, and then we are going to run it using HDFS within Eclipse and also command line, and lastly we are going to use another input file. So let me actually go through each of these, and I'm going to demonstrate, and I'll give you enough time for you guys to try this. Okay, all right, so we are going to import word count Maven project. So when you start the quick start VM, you should actually see Eclipse pre-installed. Okay, so you're going to actually start Eclipse. Okay, and then we are going to import sample project. And let me actually move forward while Eclipse is starting. So you click this guy, you start Eclipse, and you are going to import the Maven project. Okay, and these Maven projects are provided under samples Maven directory of this hands-on lab. Okay, so Eclipse is started. Yeah, looks like I have already imported. Okay, so the way you can import is File, Import, and make sure you expand Maven, and then select existing Maven project and click Next. And then you go to the browser, and you want to actually go to the directory that you unzipped this particular hands-on lab. So that's basically in my case is Cloudera, Hadoop Labs, and Hadoop MapReduce, and so this directory contains these 4 sample applications. Okay, so I can just select this guy, and then you should be able to import those sample 4 sample Maven project. Okay. All right, so once that is done, the next step I want you to do is to create, so we did that. And now you might want to build the application. So you're going to select the project. So we're going to deal with the word count. So you say word count, and then run as, and then Maven install. Okay, so you're going to actually compile Java code, and it also generates the Java file. But for now, we're actually making sure that they are compiled. Okay. So now, if you take a look at the code, you have a word count driver, word count mapper, and word count reducer. Okay. So so now what we want to do is we want to create the two runtime configuration. One is for running the application on local file system, and the other one is creating running the application on HDFS. Okay. So here we're going to actually create the runtime configuration called the word count local. Okay. So you are going to create the runtime configuration named as a word count underscore local, and the main class is this, and then you click the argument. And here you specify input and output. So this input and output should be a directory in your local file system. Okay. So and then we're going to create another one called the word count underscore HTFS. So in this case, we are going to use input from HTFS. So we provide a full HTFS path as an input, but we're going to actually use still local file systems output. Okay. So we created two. The runtime configuration. Okay, and then we're gonna actually take a look at the files. So the full file contains these two guys, these two lines of code, and bar contains the one line. So the bar is here. Okay, this is a bar file. Okay. All right, so let me see if I can import the classes. Yeah, so since I have already imported, it probably, yeah, so I'm gonna just cancel this guy. And it looks like these are all closed. I'm gonna just delete this guy and import it again just for the sake of exercise. Okay, so I'm gonna just delete. Okay, so I'm going to delete. And we are going to import it again. And then we are going to run the application. So we're going to choose the local host version first. So we're going to choose the local host, the word count local, and then run it. Then you're going to see, MapReduce application, the output. I mean, you can see a bunch of the log information, and then output will be generated on the output directory. Okay, and then you can see this. Since we have a single reducer, we have a single output file called the part all 0000, and this is the output you are going to see. Okay, so let me just demonstrate that. Okay. Okay, so let me just import the project. So existing Maven project, and Cloudera MapReduce sample Maven. Okay, so this is the directory that contains all the sample application, and so we are going to import. And I have already created the word count underscore local configuration and word count underscore HDFS configuration. So I'm going to just run it and see the result. Yeah, all of a sudden my machine is a bit slow. Now I have actually added some system out println statement to display the input value to the mapper. So you can see input value to the mapper is key value pair is actually 0, which is the offset of the first line, and this is the second line. Okay, so this is a key value pair, and then and then the second file also has a key value pair. Okay, the value, this is a bar file. Okay, and then we also display the values that are being inputted to the mapper. So the word count reducer will receive suite comma has a value of 1, and the this has a value of 1 1 and things like that. So it's basically representing how many times that particular word has occurred. Okay, and okay, so finally I get to finish. Okay, so word count. So I have already, if you take a look at the configuration, I have already created run configuration. I have already created the word count local and word count HDFS. For you guys, you might want to actually create yourself. Okay, so let me just see run configuration. Yeah, so I have word count HDFS. In this case, argument is the input is from HDFS and output is local file system. For local, as unsaved changes, yeah, so because I didn't change, I can say no. The word count local, I'm actually using both input and out from local file system. So I'm going to actually run this code, okay, the word count local. So I'm going to run it. All right, so let me just let it run, and let me just continue the to study the code. So this is a code that we have seen. Okay, so this is the mapper code, and this is the reducer code. Okay, so again, reducer code is basically the getting a list of ones as an iterator, and we'll just they create the sum. Okay, and this is the driver code. The key point in this case is that we are creating a job, and then we set the mapper and reducer class, and reducer task is 1, and then we actually check the so that is actually running the locally, so we don't have to copy any files. Okay, so it's actually running, so we don't have to copy any files to the HDFS yet because we just dealt with the local files. Okay, so let me just expand this guy. So you can see MapReduce, the task is actually performed. Okay, so you can see mapper. So this is the input files. Yeah. Okay. So this is the first file. This is the second file, and then the reducer received this guy, key value pairs. Okay. So now if you take a look at the output, we should have output directory under which we have a file that actually shows the output. Okay. So yeah, so output. Yeah, so the work is still being done. So that's the reason the output is not displaying the file. Okay, so let me see. So when it is done, it should actually say completed. Okay, so not yet. So map is not 100%, reduce is not 100%. Oh, okay, so let me see. Let me probably have to just refresh this directory. So let's just refresh. Okay, so when I refreshed, I see the output. So this is the part, and so you can see this is the result. Okay. You might want to actually change the contents of the file. So the from input directory. So those are the two files that we have provided as the input data. So I'm gonna, in this case, I'm gonna just add third line. This is the third line. This is the third line in the foo file, something like that. And you save the change, and you can actually run the application. Then you certainly should have different values. Okay, so that is actually running the application locally, meaning you're using the files in the local file system. The next one is you are going to use HDFS. So at least for input data file, we are going to use HDFS. So in this case, you have to copy input data files into the HDFS using the Hadoop fs dash copy from local command. Okay, right. So that's actually something we're going to actually do in 1.4. So you are going to you basically we want to copy the input directory into my data directory. Okay, so it should actually generate input directory under my data. Okay, and that input directory should contain two files, foo files and the foo.txt file and bar.txt file. Okay. Okay, so you have to copy these guys into HDFS as we have learned in the HDFS case in our previous presentation. Okay, and then we are going to oops, yeah, I think we are actually looking at the and then you can verify whether those two files are in fact copied. So you can actually go to HDFS name node and browse a file system, and you can actually go to my data directory, and you should see input directory, and you should see these two files. Okay, because we just copy these two files from local file system to HDFS. Okay, and then we are going to run word count HDFS configuration, and we should actually see the same result. Okay, we are still actually using output directory, the local file system's output directory, and the result is going to be the same. Okay, so you might want to actually change the contents and actually run it. Okay, so I have already copied these guys. Okay, so I have already copied these guys into HDFS directory. So I'm going to actually run, this run in this runtime configuration, and I should actually see the same result. My machine is kind of slow. So let me actually finish up the presentation so that you guys can actually do it. It's pretty slow. Okay. So let me just resume. So we just run this the HDFS. So basically input 2, we just take a look at that. Oh, okay. So yeah, I'm actually going. Yeah. So this is the result. Okay. Oh, so sorry about that. Yeah, actually I was running which. This is okay. So we are running HDFS version, word count underscore HDFS, and we can verify the result, which is still in the local file system. Okay, so same result. Now we are going to run the application at the command line. So command line, as I said before, the default file system is HDFS. So we are going to use the jar file that gets created. Again, when you perform Maven install, you create a jar file. Okay, so it should actually generate the word count 001 snapshot jar file. Okay, and let me just take a look at the. We're gonna just run it. Yeah, so I've already done this. So I'm actually taking a look at the target. If you go to target, you can see it generate the jar file. Okay, so that is the word count 001 snapshot.jar file. Okay, so it's generated. So what we are going to do is we are going to run this, the MapReduce application at the command line. So we are going to use, first of all, we are going to make sure you are in the word count directory. Okay, so I'm going to copy this guy. Let me just. Wow, this is somehow I'm gonna just okay. Yeah, let's just use the existing command line terminal window. So you want to make sure that you are in the word count directory, because you are actually specifying the target directory and the jar file like this. Okay, so open it. I'm going to just open the terminal window and making sure that I'm actually in that word count directory, and then I'm going to run this code. Okay, so here, this is the default. So I should have a my data input directory on HDFS as well as the output directory on HDFS. Okay, so once you have run it, this is what you're going to see. And then you can actually take a look at the input directory, and output directory should be created here. And when you actually take a look at the output directory, you should see part all 0000. And again, when you take a look at the contents of it, it should actually show the result. Okay. The 1.7 is, instead of actually using those full.txt and .text file, you are going to use the tomsawyer.txt file, which is a bit bigger than those two files. So here you are going to copy this file into HDFS. Okay, so you're going to say Hadoop FS copy from local input my data. Okay, yeah, basically in this case you're copying anything on the input2 directory in local file system into my data. Okay. And then you make sure that file is now in HDFS, and then you can run this code. Okay, so let me just do that. So I'm going to just run this guy because I have all these files already in the HDF5. Okay, so let me just go to that directory, and then I'm going to run copy and run it. And once it is, at this point, you can actually go to the job tracker node, and you can actually find the, running map tasks. Okay. And then you should actually see output2 directory gets created as an output. And then you can take a look at, again, part all 0000. And then, this is basically the all the words and the occurrences of those words in that tomsawyer.txt file. Okay. Yeah, so my machine is pretty slow, but it should be running. Okay. All right, here we go. Maybe I should actually restart this virtual machine. Somehow things are actually pretty slow. The concept of input files and input format, we touched upon this on a little bit. Okay. So input files, this is where the data for MapReduce task is initially stored. Oh, okay. I think I didn't answer one of the questions that was asked, where the jar files are supposed to be present. The question was, do these job files need to be in HDFS or a local file system? Okay, and I kind of give you a quiz for you guys to think about it. If you're running within Eclipse, because you're dealing with a local file system, it could be actually in the local file system. However, if the data files are involved in well, actually, the answer is actually has to be on the HDFS. So because the code has to be moved around to a task tracker, right? Okay, so the job file need to be uploaded to HDFS, and that's actually done by Hadoop. Okay, all right. So hopefully that answers your question. So input files, this is where the data for MapReduce task is initially stored. The input files are typically reside in HDFS for scalability and reliability reasons, as we talked about. The format of these files are arbitrary. So, in our exercise, we dealt with a text file, but the format of these files can be binary files, okay? So line-based log files can be used. We could use also binary format, multi-line input records, and something else entirely, meaning even binary file is actually it could be actually read. It's very typical for these files to be very large. We are talking about tens of gigabytes or more. Now, input format. So how these input files are split up and read, defined by the input format. Okay, these input files are not moved around. They are actually located in the data nodes. Okay, which task tracker will actually handle which which files in which data node. I mean, that's actually the role that input format class is doing. So input format is a class that provides the following functionality. So select the files and other objects that should be used for input. It defines input splits to break the file into tasks. Okay. It provides a factory of record reader objects to read the file. So these are all done by Hadoop. Okay. The several input format classes are already provided by Hadoop, but you can certainly provide the custom input format classes. So the one we have worked with is the text input format class, and that's in fact the default. Okay, so unless you actually specify different input format class in your in your job, okay, it will use a text input format class. There is a key value input format that is actually reading things in the key value format, and sequence file input format that's actually for reading binary file. Okay, so the default behavior of text input format class is that it treats each line of each input file as a separate record and performs no parsing, meaning it will just take the contents. So these are these three different input format classes: text input format, key value input format, and sequence file input format. So again, text input format class is a default format. These are lines of text files. And in this case, the way it's going to read each line is the byte offset of the line is a key, and the value is the line contents. Okay. In the case of key value input format, it parses the line into key value pairs. So everything up to the first tab character. So it's using tab as a delimiter, and the remainder of the tab is going to be set as a value. And so sequence file input format is actually the most free format in a sense, and the key value pair could be actually defined by user class. Okay, so I'm going to actually finish up the presentation, and then I'm going to explain the hands-on lab, and I'll let you guys have time to do the lab. So here we're going to actually do exercise 2 more sample application. That exercise 2 is the world size application. Exercise 3 is the weather stat application. Okay, so that is in fact the end of the presentation. So let's take a look at the lab documentation. MapReduce. So we have 3 more exercises to do. So exercise 1, we just did it. Exercise 2, actually 2 more exercises. So in exercise 2, we are going to read the same text file, and this time what we want to do is we want to actually count the size of the words. So in this case, the end result, something we want to do is that we want to find out, any word whose size is 2, we want to find out how many times it has occurred. So the output is something like this. It means that for the size of 3 characters, it occurs 4 times. For the size of 4 characters, it occurs 4 times. For the size of 6, it occurs just once. Okay, so we want to read the text file, and then we want to actually count, of the words based on the size, okay, rather than based on the word. Okay, so it's pretty similar to the exercise 1, but we are going to see how we can actually modify the code. Okay, so again, you run the code, and you should actually see the result like this. Okay. So here we are going to run the application using HDFS. So we have to, so in this case, we are going to actually build this application using Maven command. So instead of using Eclipse, we're going to actually just build it in the command line. Okay, so let me just go over here, and so this is the word size. Okay. And we are going to actually build Maven install. So we are going to create a jar file. So jar file has been created, and then we are going to run this code. Okay, so jar file has been created successfully, and then we are going to run this word size code. Okay, so I'm going to just copy this guy. So we're actually using the same data. So copy and then run it. And then, so here output 2, that should be the in HDFS. Okay, so we're going to actually take a look at HDFS output 2. Yeah, so that's what we're going to do. Okay, so let's actually wait until this is done. And you can take a look at the output 2 directory. It should have a part of 00000, and it should, it should actually give you the size of 1. It happens, it's probably A, 2483 times. Okay, so let's actually take a look at that. So we go to, I'm going to actually go over here, and HDFS name node, and go to browser file system, and we go to user, Cloudera, and output 2, and so this is the this is done. So you can see the time is Pacific time 1:04, so that's just a few seconds ago. So I take a look at the output, and as expected, this is what we see, which is good. So it worked. Okay, now let's take a look at the code. So this is a mapper. So in this case, we are basically generating this key value pair for the size and sang. So for any word, we are going to actually generate the size of it. Okay, for sang, it will have a 4. For the A, it will have a 1 and A, or something like that. Okay, so one of the exercises I'm going to actually ask you to do is, you are going to actually insert printout statement to see the input values to the mapper and input values in the reducer, as we have done in exercise 1. Okay, this is a reducer. So in this reducer, we are basically again sum things up, right? So as far as the reducer is concerned, this is pretty similar to what you have seen in exercise 1. However, you can actually see the input and output values are a little bit different. So in this case, it's a text input. It's a text input writable and text input int writable. Yeah, so you have to actually okay. So this is the from exercise 1, right? And then we have the reducer. This is the new code. So this is int writable text and int writable int writable. So basically, what you receive is we're actually receiving the size of the size, like a for 3. We'll have a list of all the actually the text. So size 3 and text, and then you're basically generating the size, which is int writable and int writable. So you can see the type has to be changed. Okay. because the output in this case is both the int value. Okay, so that is the reducer, and in terms of driver, it's pretty much the same. Okay, and you have to actually specify the key value pairs, okay, correctly. And other than that, it is the same. So you might want to actually have this system out println statement to see, input values to the mapper, input values to the reducer. Exercise 3.1.3 is now we, instead of using text file, we are going to use the weather data. Okay, so the input data you see under so if you actually go to let's say weather here, so input data in this case is, oops. Oh, that's sample text. Is that sample text? Yeah, okay, so this is a sample text, and this is actually a very small size of the weather data. And the thing is that this is the year. So we have a year, and then we have a bunch of information. But what we want to find out is the air temperature. So in this case, this string, this 4-digit string represents the air. So we have information about 1950 and 1945, and this red colored value is actually air temperature, average air temperature for that particular year or month, probably a day. Okay, and then this one is representing what is the blue colored single digit represent air quality. Okay. So what we want to actually find out is that, we want to actually find out the average air temperature for the year. Okay, so we have 3 values for 1950 and we have 2 values for 1949. But in real life data, you probably have the thousands or even millions of lines with this information. Okay, so in this case, this is a mapper code. So we basically get the line. So it will receive each line. Okay, each line as an input. So basically what we want to do is we want to subtract the temperature value and we want to subtract the year value from the substring. Okay, and then output is going to be the year and then the air temperature value. Okay, so that's the mapper. Reducer will actually receive in the form of the text and input writable. So in this case, basically, we are just finding out the max value of each of those year. Okay, and then we are going to actually write the key value pairs. The key is going to be the year, and this is going to be the max. You create the max, you find the max value, and then you are writing the max value. Okay, and the driver code is pretty much the same. Okay. So, first of all, you can actually build and run the weather status Maven project. So I'm going to just build it as a Maven project at the command line. So we are going to weather, and let's actually Maven install. So we're going to create a jar file. Okay, and we are going to actually run input and output too. So let's see. Yeah, so this is actually running locally. Okay, so I'm going to actually move forward and we're going to actually run it in the HDFS. Okay, so I'm going to just move forward. So first of all, we have to copy local data set to the HDFS via Hue. Yeah, so in this case, we're going to use the Hue, but you can just use the command line tool as well. So here, the thing we need to copy is basically the file we need to copy is, so we are going to actually create the my weather data directory. Okay, so let's actually see my weather. Okay, so I'm going to just copy at the command line. Okay, so Hadoop fs make dir, and we're going to just create the root level my weather data. Okay. Oh, so in my case, it's already existent. So so I'm going to move forward. So I have that, And so I have done that already, and click yes. So I should have, I can actually see the data. So let's actually take a look at the my weather data directory. So I'm going to say ls, and we should have we should have two files. One is the 1901 and 1902. So let's take a look at the contents. So I'm going to just say cat and go to the end, and then I'm going to copy 1901. Okay, so it just contains this. Yeah. Oh, it's pretty well. Yeah, this is actually relatively good size of the file. Okay, so I have already have done that. Okay, so we are going to run this code. So we copied all these files. Yeah, so we have those files on the HDFS, and then we are going to run it. So I'm in that directory. I already have done Maven install. Okay, so I have created a job file. And then I'm going to run the the application. So okay, so I'm going to run the application, and it should actually generate the output in output2 directory. Okay, so we should actually, so this is the result. Okay, so we can actually, we are taking a look at the that output file within Hue. Okay, but you can take a look at the from HDFS web UI. Okay. Again, you can insert the sysout println statement to see input data into the mapper and input data to the reducer. And if this MapReduce programming model is a bit confusing, don't worry about it. As I said before, this is rarely used because it's rather complicated to build a Hadoop application using MapReduce Java Programming API. Instead, in general, you're going to use a high-level API such as a PIC and HiveQL to do, the Hadoop operations. Okay. All right, so it is done. So I'm going to just use the HDFS name node. So it's output 2. And go to the browser file system, and you go to user, Cloudera, and output 2. And so this is, again, it's 134, right? So yeah, so it's done just a few seconds ago. And if you take a look at the output, this is the average temperature of 1901, and this is average air temperature on 1902. Okay, so it actually shows you it worked. Okay. All right, so that is the end of this presentation. We have actually 5 minutes, so I'm gonna just stop